All good from my side.
Yep. Okay, so hi. For those of you I didn't have the intention yet to talk with, my name is Laura. I started in March last year my PhD at the University of Antwerp at the research group, which is also a collaboration with the company IMEC. Not sure if you're familiar with that. And so today I will present a first small work that I have, that I've been doing, which is also now an archive already. So if you would be interested, you can of course take a look at it afterwards. Which is a simple extension to the training of the hyperdimensional classifier. And for that, I will use a threshold on the confidence of that classifier. Is this working? No. I'll just do this. I will give a little bit of an introduction to my talk, like why we looked at extending that training procedure. So hyperdimensional computing, last day we already talked about its benefits, right? Like we don't need that much data to train. It's very robust to noise. It has low latency, fast processing, less complex. Probably I'm still forgetting some, of course, but we have discussed it, so I will leave it as that. And so that's why it's suitable for wearable IoT devices, near sensor AI, and on-device processing. And that is also one of the motivations why I'm looking at HDC. But of course, then you have the downside that it's often still not performing as good as those, deep learning models, let's say. So that's why we were looking at how to adjust and improve such HDC classifiers. And so, as I said, I am interested in the wearable IoT devices applications. And so that's why I'm also only looking at binary vectors up to now, and also the dense representations for now. Maybe later they will be more sparse, but now dense binary of 10,000 elements. And so this is my introduction. And what did I do? I did it simple, but I will show you it was effective. Extended training procedure for the binary HDC framework. And I tested it on several applications that would be suitable for wearable IoT devices. The overview of HDC, I don't think I will need to explain it in much detail here, but just to make sure that we are on the same page, you start with the mapping of the basic objects, you encode your input data based on those atomic vectors. You do the initial prototype construction by adding vectors of the same class. And then the training, we only use samples that are wrongly classified. We add them to the correct class again, and we bundle them out of the wrong class. All good. But we were thinking, okay, like why only use wrongly classified ones? Because it could be that a sample is correctly classified, but that similarity of that correct class is just slightly higher than the similarity of the second class. Like what then? Like it could be that in a next iteration, that sample would be misclassified, or with a different initialization of your system, that it would be misclassified with a bigger gap in similarity. So I was not the first that was like thinking this way. There was a paper of Duan, I think, that addressed this point, but they were using then a binary neural network. They were mapping the HDC framework towards an equivalent binary neural network, and then they mapped it back. But as I said, I want to be as simple as possible. I want to have that wearable IoT device application at the back of my mind. And I don't want to use such binary neural networks, at least not at this moment. So that's why we try to approach it differently. Namely, we just introduced a confidence metric, but again, I was not the first one. I will explain a little later. Let me first introduce that confidence metric. which is just the difference between those two highest similarities. So as I said, we are only looking at the correctly classified samples at this point then. So this corresponds to the similarity to the correct class, and then this one to the similarity of that second highest, the second highest similarity. And so, as I said, there was a paper of Huang, I think I pronounce it, but they used this confidence metric only at inference time. They had like a binary HGC model trained and also a non-binary HGC model, and they always tried the classification on the binary HGC and looked at inference time, how the confidence was in that of that binary HGC model. And if that confidence was not that high, then they switched to that non-binary HGC. But then I will stress again, I want to work on a binary HGC framework, and I don't want to look at those non-binary cases, as of my perspective at least. And so that's why we use this confidence metric not only at inference time, but we will use it during the training, during the updating of those class bundles, to really improve the binary HGC model and not just switch to another trained model. And so then actually we just said, we still keep the correcting of the wrongly classified samples, so that we just extend it. Like if your predicted outcome is your correct outcome, but that confidence metric is lower than a certain threshold, we will actually treat them as a wrongly classified sample. We will also update the class bundle of the correct class, and then the class bundle of the second highest similarity that we found. And then this L prime is then the class with that second highest similarity. So that's what we did. Just using that confidence metric that was already introduced before in the literature, but to make our binary HGC model better, let's say. And for this, I looked at 4 data sets. I think the isolate and UCI human activity recognition data sets are already previously being used in the HGC framework. The CTG one is not that much used, but it was a smaller one. And so we just wanted to see, does it also work on smaller data sets? And then this is the hand gesture data set of Abbas Rahimi. And so we did the record-based encoding for this. And I did the mapping of vectors to 21 level vectors. And as I said, we introduced a threshold on that confidence metric. So to decide which thresholds we should test, we looked at the confidence metrics right after the initial prototype construction to see how confident we are after the one pass training. And as you see, the confidence in percentage is not that very high. Like it's at maximum here of 8%, here even only to 5 or even 3.5. But so we decided our threshold settings, and these were the ones that we will test. So these were then our results. I did the training for maximum of 2,500 iterations, but I checked after each 100 iterations whether the train accuracy was already higher than 99%, because it was not always needed to train that long. And I did 50 independent runs because of the randomness of HGC that we all know. What was very interesting is that for each of those threshold settings, we saw that the baseline accuracy, which is the 0 one, because 0 it means that we just do only the wrongly classified samples, but not the correctly classified ones. And so it always improved for all the thresholds. Of course, for the CTG, we started low, so we had still much more room to improve compared to the other ones. But if you looked at the error rates, we always had like a relative 20% increase, or a decrease in error rate, so increase in performance. And also we saw that the accuracy always improved towards the best alpha value, let's say, then it decreased, but still it was higher than our baseline. But not only based on the accuracy, we could see the improvement of our method, let's say. We saw that also when we looked at those confidence distributions. Like here I show both for the baseline, so the alpha equal to 0, and then the best alpha, like the alpha that gave the best accuracy. And here we saw that for the baseline cases, the alpha value, the confidence values were here already less prominent in our samples, but even for then the higher alpha, especially here we see that, yeah, below that threshold, everything was gone and the whole distribution shifted towards higher confident values. So it's not that we improved our accuracy, but we also improved how confident we can be in predictions that we made, let's say. And that brings me actually already to my take-home message. Like, we did a simple extension to that training, that updating procedure of those class prototypes, but it was effective. And yeah, we had more samples that were correctly classified, but we were also more confident in those classifications. But of course, yeah, we just wanted here to show you that that simple method works on its own. But of course, as I will go back to my previous slide in a moment, but we could also take a look at like maybe adapting the threshold while we are doing those training iterations, because as I said, as I said here, you see clearly here the line of below alpha equal to 1, everything, like there are no samples with a confidence lower than 1 and everything is shifted towards the right. So maybe we should shift our threshold along, because at some point there will be no samples below 1 anymore. So that is one thing that we were thinking about, maybe make that adaptive in some way. And the second thing is, of course, there are also other methods already that try to improve that training, that updating of class prototypes in some way. I list here a few. You have the large margin perceptron of Dimitri here, that also used more errors, dual training. I think Rahimi added sample vectors only if the similarity was not that high already, and then adapt HDF, online HD, man HD. So I'm not saying that my method is the way to go now, and I'm also curious to see when we combine it with other methods, whether it would still improve more or not or whatever. So I think it's a nice view on some future work on this. And so that was my talk.
Thank you, Laura. Still questions? Dennis, you also?
For prototypes binarized, have you had the binarization step or will it continue?
Let me I always update the non-binary class bundles, but the similarity check is always to the binarized vector, or so that I can still use the Hamming distance.
Binarized one and inference is done to binarized one.
Yes, indeed. Yeah. So the similarity, and that's why I use here a lowercase. Those are the vectors, but here I update the bundles, let's say.
Yeah, but I think the question was whether you binarize the bundles at the end, or
after when I put like in each iteration at the end. So I fill in, I give all my training samples. I do all the updating, and then I binarize again, and then in the next iteration I start again looking at the similarities compared to the vectors of the previous step, and so on. If that's the answer to the question.
I have some brief remark. So when hyperdimensional computing became to classify, for some reasons, most of work used some prototypes. That is the most naive approach. Then they have some kind of revolution, or that is eventually let's use a perceptron rule. but for a long time we used similar but not identical algorithm to, that proposed by Laura, and actually it performs somewhat 20%, let us say, in general, better than usual perceptron. So why not use that instead of perceptron? So I think now everybody will use this version. This is we consider it as an analogy to large margin perceptron, or eventually approximation to support vector machine, because it separates not randomly but with some margin those tests, those data of different classes. And for example, of course, it is not theoretically so sound as support vector machine. But when I use hypervectors with a dimensionality of 1 million, I cannot, for example, on MNIST, I cannot wait for support vector machine to converge, or wait a day or two, several days. And here we converge in several minutes. By the way, I never used more than 200 iterations.
No.
Don't wait until convergence. I just use fixed number of iterations or convergence.
Yeah.
So, no, but
that's a design choice. Yeah.
Details we'll discuss further. Thank you.
Yeah, but sorry, to make a little bit more of an extension, like indeed he approached me and said like this looks very like the large margin perceptron, and then also like a soft margin SVM, because as a soft margin SVM allows more errors in its system, and that's actually what we also do here. Like we don't just make the we don't make the hard line between correctly and wrong. We just have a slightly in the boundary layer of that classification part. We allow more errors to be corrected, or actually basically. So yeah.
I just had a naive question that is also related to like the support vector machine idea, because like as I understand, this algorithm and SVM would work perfectly if there's like a linear classification that needs to be done. But then the data might not always be linearly separable. So I was wondering if people use kernel tricks in SVM to get around that, and I was wondering if you were thinking about that for these kinds of data sets, or like an equivalent of
I've been reading about and also discussing with a colleague of mine at another university about those kernel things. But to be honest, it's not really into my knowledge, let's say. So that's why I will not, I think, directly jump into that specific thing. But I'm not sure if you are interested in that. Of course, you can take a look at it. But for me personally, it's not now what's on my menu.
For sure.
If I can answer your question like that. But I'm not saying it's not interesting, of course. So it's definitely worthwhile taking a look at it.
Thank you.
Ross?
I was just going to say it might be useful conceptually to interpret what you're doing as being as treating it like a statistical modeling problem, following on from what Chris was saying. But thinking of it as what's happening is you've got a data set, you've got features, you've got cases, and you're applying a weight to the cases, and you're reweighting the cases so that the cases are as close as possible to the border, have the highest weight because they're the most informative as to the location of the border.
Yeah, and that's also what I just said with that boundary layer. It can be that they are so close to that boundary layer where we now put the class discrimination, let's say. And indeed, like it could be that they are in the next iteration, just like they get to different positions.
All right. If you're all happy, let's thank Laura again.